Chapter 10 dealt mainly with the concepts involved in computer file systems. Now, in Chapter 11, we get a little bit more into the details of how those concepts can be and are actually implemented. How are files actually stored on a disk, which is the most common secondary storage medium? How are directories implemented? What is a file allocation table? These are all things we consider in Chapter 11. Even though nowadays we have optical disks, USB drives, and flash-based solid-state drives, among other storage technologies, a lot of the details of how we implement file systems are tied to the characteristics of magnetic disks, hard and floppy disks, because historically, those were the media that file systems were built upon. Disks can be read any number of times and can have information overwritten with new versions of the same information or all new information. Disks can be accessed directly by moving the heads, the read-write mechanisms, in and out radially, and or by allowing the disk to rotate so the desired information passes the heads. Another characteristic of a disk is that we don't normally read or write individual bits or bytes of data. It's not efficient. Because of the nature of the media, we read or write entire sectors at once. Disk sectors are all the same size in bytes regardless of where on the disk they are located. A typical sector size is 512 bytes. This is normal for disks that are intended for use with MS-DOS or Windows. It could be larger or smaller, but for a given disk drive, it's a constant number. We access the disk by sectors or by groups of sectors called blocks or clusters. These also are of a fixed size. A file system has multiple layers to it because it has to provide a certain view to the user at the high level, but it has to interface directly to the hardware at the lowest level. The user and the user application see the logical view of the file system. The intermediate layers provide a mapping from the logical view to the physical implementation. The number of layers and the exact way the functionality is divided up among the layers varies from one file system to another. There is no one right way to do it. There are more file systems in use than there are operating systems, and most operating systems support mounting multiple file systems. So, what does it take on an actual disk to implement a file system? A volume, or logical drive, can be bootable or not. If it is to be bootable, then it needs a boot sector or boot block that contains code and other information needed by the CPU to boot the operating system. In addition to the boot block, each volume needs a volume control block to contain information such as the number of storage blocks, sectors or clusters, the size of each block, the number of free blocks, pointers to free blocks, and so on. A directory structure is built for at least the root directory of the volume. Other directories can be built under that. Each file within the directory has a file control block, or FCB, associated with its directory entry containing information about it. What's in a file control block? It varies from one file system to another, but typical information that might be included in a file control block might include these kinds of things. For performance reasons, some file system data structures are kept in memory for quicker access. These might include a mount table with information about each mounted volume, a cache of recently used directory entries, a table of FCB information about all the files that are open, a table for each process that keeps track of the files it has open, buffers to hold blocks of data being read from or written to disk, and so on. Creating a file involves allocating a new FCB. The system reads the directory into memory, updates it with the new file name and FCB information, and then writes it back to disk. Once a file has been created, it can be opened, and then read or written, and eventually closed when we are done with it. When we open a file, our code passed a file name to the logical file system. The call to open checks the system-wide open file table to see if the file is already in use. If it's not, the directory is searched to find the information for that file, and when it is found, the FCB is copied into the open file table, which is system-wide, and is also entered in the per process open file table. When we do open a file using its name, the system normally returns a number, allowing us to use it to access the open file for reading and or writing. This number, or identifier, is variously called a file handle under DOS or Windows, or a file descriptor under Unix and Linux. The open function also returns us a pointer to use for reading or writing the file. This slide shows how the data structures kept in memory can be used to effectively cache the directory structure on the disk and provide access to the file control block FCB information for each file, and ultimately to the data blocks for the file itself. When we boot a system, we have to mount at least one file system just so the operating system can find the files it needs to load itself. We refer to this as the root partition of the boot drive. Additional volumes can be mounted at boot time or later. When multiple file systems can be mounted by one operating system, how can we integrate all of them into one directory structure so users can access them all seamlessly? One approach is to use an object-oriented paradigm to simplify and abstract the implementation details. We can have a generic file system interface that connects to the VFS, or Virtual File System Interface, with the specific details of the various file systems hidden at the lower levels. This gives application programs a consistent interface no matter what the underlying file system looks like. It could be a hard drive, a floppy drive, a flash drive, a network drive, or whatever. Linux is an example of an operating system that implements a VFS. It has 4 object types that relate to the file system, and each of those has certain operations that can be implemented on it. Linux has superblock objects that represent entire file systems that can be mounted and unmounted. D-entry objects that correspond to individual directory entries. inode objects that represent individual files, and file objects that represent files that are currently open. Operations or functions can be called without knowing anything about what type of physical device the file is stored on. How do we implement directories on a disk? We look at that now. The simplest method is to use a linear list. Simple to program, that is. It is not the most efficient structure to search through if there are lots of files in the directory. We have to search the entire list when creating a file to avoid duplicate file names. We have to search it again to delete a file, and we have to have a method to free up space in the directory and reallocate it when files are deleted. We might want to implement the directory as a sorted list, but the need to resort it every time we add or delete a file adds overhead. To make the lookup of directory information more efficient and quicker, we can add a hash table that takes a hash value computed from the file name and uses that to look up the file's information. Of course, we need to be able to handle collisions, and it's hard to have one hash function that works for an arbitrarily large directory. We may need to enlarge the hash table. When we implement a file system on a disk, we need to have a system for allocating space on the disk to files in such a way that space is used efficiently and files can be accessed quickly. There are 3 methods that are commonly used for space allocation in file systems, and we look at those methods now. The most straightforward implementation, conceptually at least, is contiguous allocation. In this approach, each file is stored in a set of consecutively numbered sectors or blocks on the disk drive. It is conceptually simple in that all we need to know to access a file is where, or what block number, it starts, and how long it is in terms of the number of blocks. Since all the information within the file is in consecutive disk blocks, and since consecutively numbered disk blocks are normally physically adjacent, this approach can give good file system performance in terms of minimum time required to read or write the file. While accessing an existing file is easy and quick, though, there are some problems associated with contiguous allocation. First of all, it can be difficult to find space for new files. If a file needs 1,000 blocks of storage, we could conceivably have several contiguous regions of 900 or more blocks and still have nowhere to put the file. And then, assuming that we do find a contiguous block that is large enough to fit the file in its original size, what if we later want to append information to the file, making it larger? We may have to move the entire file to a new location where more space is available, which can be time-consuming and inefficient. The process of fitting files on the disk ends up giving us many of the same type problems as fitting programs into memory did back in section 8.3. We can wind up with a great deal of external fragmentation where we have little pieces of unused disk space that are too small to hold most files and so are wasted. We could move files around to compact the wasted space and create larger holes to put new files in, but again, this can be a time-consuming process. We would probably only want to do that when the system is unused or very lightly used. Here is an example of files stored on a disk in contiguous blocks. Notice the empty spaces between files that will be wasted if we don't create another file small enough to fit within those contiguous spaces. On the bright side, we can see from the directory that very little information must be kept about the files, only their starting block and their length. Many newer file systems use a modified contiguous allocation scheme. The modification is that files are initially given an allocation of all contiguous disk blocks, but if the file eventually needs to grow beyond that allocation, the file may be given an extent, or extension of space, which is itself contiguous, but may not be contiguous to the original file location. To be able to reconstruct the entire file, the original extent plus the newly added extent, we need not only to have the start and length of the original allocation of the directory, but also a pointer or link to the first block of the next extent. To get around the observed problems of contiguous disk space allocation, we can use linked allocation. This is more complex to implement because the set of blocks that are allocated to a file are kept track of in a linked list. The directory contains a pointer to the first, and usually last, blocks allocated to the file. Each intermediate block contains a pointer to the next block. The use of the pointers means that the disk blocks allocated to a file need not be contiguous. They can be all over the disk if need be. For example, a file might start at block 9, then continue at blocks 16, 1, 10, and 25, as shown here. The external fragmentation problem disappears because we can use any block anywhere on the disk anytime for any file. We never run out of space to put new files, regardless of their size, until the disk completely fills up, or in other words, all blocks have been allocated. Linked allocation is not completely without issues, however. It works well for sequential access files, but not so well for direct access files. The pointers themselves take up space on the disk, which takes away from the space available for data. And of course, we have the processing overhead of traversing what may be a long linked list for a large file. We also can have a reliability issue since if any of the intermediate pointers become damaged or corrupted, the rest of the file becomes impossible to locate without searching through all the blocks on the disk and knowing that you have found the needed block if indeed you do find it. There are approaches to mitigating this risk using a doubly linked list or storing extra information with each pointer, but those add further overhead to the scheme. One variation on linked allocation that is very widely used, due to being implemented by Microsoft, is the use of a file allocation table, or FAT. Original MS-DOS supported FAT12 for floppy disks and FAT16 for hard disks. FAT32 was added later to support bigger drives. The numbers refer to how many bits each FAT entry takes up, which limits the maximum number of clusters on the drive. Rather than store the linked list pointers in the disk blocks used for data, they are stored in a designated area of the disk dedicated to the FAT. The table itself is used much like a linked list, with each entry pointing to the entry for the next cluster. Here we see that the directory entry points to the first cluster's FAT entry, and then it points to the second, and so on. The last entry contains a special end-of-file marker, so we know it's the end cluster of the file. Unused clusters have 0 in their FAT entry, so we can easily find them when they're needed. Because the FAT itself is allocated contiguously, it is relatively easy to cache and search through. Another attempt to solve the problems of contiguous allocation is indexed allocation. In this type of system, every file has an index block that contains pointers to all its data blocks. The pointers are arranged in order so as to access block I of a file, we simply need to find the ith pointer in the index block. This makes direct access files just as easy to deal with as sequential access files. There is no need to require contiguous allocation and no need to traverse a linked list. The directory entry simply contains a pointer to the index block, which in turn tells us where the data blocks are. In this case, block 19 has pointers to the 5 data blocks, 9, 16, 1, 10, and 25, with additional pointers set to -1 to indicate unused. There is overhead in the scheme because every file needs an index block, even if the file itself is only 1 block long. So if we have a lot of very small files, we could waste up to 50% of the disk storing index blocks, which have to be relatively large because files can be very large. In fact, if files can be arbitrarily large, we are never guaranteed that any fixed size index block will be big enough for the largest files, but it may be way too big for the smallest files. One size definitely does not fit all here, so we need some additional mechanisms to handle these issues. One approach to keeping index blocks themselves small but allowing files to be large is to allow multiple index blocks to be linked together and used for the same file. We can have the last entry in an index block be either a null pointer for small files or a pointer to the next index block for larger files. We can link together any number of index blocks to allow access to arbitrarily large files. This approach is essentially a hybrid of indexed allocation and linked allocation. Another approach is to have 2 or more levels of index blocks. The first level block contains not pointers to data blocks, but pointers to second level index blocks, which in turn point to the file's data blocks. Depending on how big we want to allow files to be, we might even have a third level, pointers to pointers to pointers to data blocks, or even a fourth level, pointers to pointers to pointers to pointers to data blocks. Each additional level essentially increases the maximum file size by another multiple of the basic block size. So if a block size is equal to 512, or 2 to the 9th, and one level lets us access a file up to 512 squared, or 2 to the 18th, or 256K, then a 2-level scheme would allow files up to 512 to the 3rd power, or 2 to the 27th, or 128 meg in size. And adding a 3rd level would allow us to have files up to 512 to the 4th, or 2 to the 36th, or 64 gig in size. Of course, there is some overhead associated with following the chains of pointers, but overall, this is a pretty good approach to handling a wide range of file sizes. Graphically, this scheme looks somewhat like the next slide. Here we see the multiple levels of indexes that eventually point to the data blocks of the file. To more easily handle a variety of both large and small files as efficiently as possible, we might combine the 1-level, 2-level, 3 and maybe even 4-level indexed allocation schemes into one implementation. We can have an index block that contains certain directory information about the file, plus a number of direct blocks that contain pointers to file blocks. For a small file, these might be enough. But then for medium-sized files, we also have a single indirect pointer that points us to a second-level table of pointers. And then for larger files, if we need it, we also have a double indirect pointer that points us to pointers at the second level that point us to third-level tables. And to handle extremely large files, we also have a triple indirect pointer that allows us to add that extra level. We only use the higher levels of indirection for very large files. They are there if we need them, but if not, we don't have to use them. This keeps the overall scheme as efficient as possible in handling small, medium, large, and extremely large files. This particular slide is taken from the UFS file system used under Unix. It's the structure of an inode. When we first format a disk, all the data blocks are free. As we create files and use blocks, we need to keep track of which blocks are used and which blocks remain free. If files are deleted, we need to add their formerly used blocks to the free list, unless the disk is a write-once medium like a CD-ROM or DVD-ROM, in which case, once we allocate a block and use it once, it can never be used again. In other words, to do free space management, we need some sort of a free space list, a data structure to keep track of which disk blocks are not currently in use. These are the blocks that are available to be used when new files are created, or existing files need to grow in size as information is added. One approach is to use a bitmap or bit vector. It's a simple approach. We just keep one single bit for each block on the disk. 1 means the block is free, 0 means it is in use. This is not only simple, it makes it easy to find the first free block or any number of consecutive free blocks. It is also supported by bit manipulation instructions that are part of many popular processor architectures. It does mean we have to keep a fairly large bit vector in memory for performance reasons, while also updating it on disk for reasons of recovery if the main memory loses its contents. Another approach is to use a linked list to manage free space. We keep a pointer to the first free block, and then that has a pointer to the next one, and so on. It's not efficient if we have to traverse the whole list, but fortunately that's not something we often need to do. This can work well if we just need to find the first free block, but it is not well suited to file systems that need to allocate contiguous blocks. Grouping is a variation on the linked list free list approach where the entire first block minus 1 is used to store the addresses of free blocks. The last entry is used to point to another block with the addresses of more free blocks, and so on. This approach allows a large number of free blocks to be found quickly. Counting is an approach that takes advantage of the fact that, in general, several contiguous blocks may be allocated or freed at one time. Instead of keeping a complete list of free blocks, we keep the address of the first free block and how many follow it. Then the next entry keeps track of the next non-contiguous free block and how many follow it, and so on. Each entry requires more space, but due to the contiguous space there are fewer total entries. So overall, this method can be more efficient than a pure linked list. In a real system, we not only have to have an approach that works, but we have to come up with an implementation that performs in the real world. The potential problem is that disk performance itself is slow and tends to compromise the performance of even the best algorithms. The main parameters are the efficiency of disk space usage and the overall performance or speed of accessing information that's stored in files. Here we deal with various things that can be tweaked to try to increase either efficiency or performance in real systems. Efficiency depends on disk allocation and directory algorithms and the types of data that are kept in each file's directory entry. The more information we keep track of, the less efficient the scheme is. The more space we waste keeping track of needed information. Clustering, or grouping of blocks, tends to increase performance at the expense of also increasing internal fragmentation, wasting disk space. In a system with virtual memory, we need to account for the fact that main memory is not only used to cache items buffered from disk or secondary memory, but main memory is also used to provide space for memory-mapped I/O operations. We can use a page cache to hold pages containing file data as pages rather than as file system blocks. This can be done for both code and data and is more efficient than interacting directly with the file system. This is known as a unified virtual memory. Solaris, Linux, and Windows use this technique. Some operating systems, for example Unix and Linux, provide a unified buffer cache to cache both memory-mapped pages from disk and file system I/O. This allows the virtual memory system to manage file system data as well as regular I/O operations. This is a more efficient system than otherwise. If a unified buffer cache did not exist, then we have this situation where memory-mapped I/O has to go through two caches, the page cache and the buffer cache. This double caching system adds overhead and wastes memory. It can also lead to file corruption due to discrepancies between the caches. On the other hand, when we use a UBC or Unified Buffer Cache, then both memory-mapped I/O and system calls like read and write use the same page cache. This makes the overall system more efficient and avoids double caching. Taking out the middleman, the extra page cache, is what makes the overall system more efficient. This concludes our discussion of Chapter 11.